All right, everyone, we are back, and I want to go through and do an even more, I think, challenging problem here, which is requiring us to do kind of some statics work. So let's go ahead and let's first draw out the free body diagram. I think we're getting good now at kind of defining, our coordinate system and our boundary conditions. So let's say that this is x equals 0, this is x equals L. So I have here, there's one force here that's 10 kilonewtons. I have one force here, 1 kilonewton, or 1 newton, excuse me. There's going to be another, and actually this is the opposite direction. So there's going to be another force here, force of y. There's going to be a moment, because the beam's going to go this way, so there's going to be a restoring moment this way, m. So I'm going to go ahead and solve for those. So the sum of the forces in the y must be equal to 0. So we have plus, which is equal to 10 times 10 to the 3, minus 1 minus f of y. We have, I'm going to do the sum of the moments around here, sum of the moments around the origin. So that's going to give us that, f of y is going to be equal to 9,999 newtons. Sum of the moments around that point, 0, is going to be equal to, so we have that moment that's going counterclockwise, right? Yeah, so we have this plus m, because we're going counterclockwise, I'm just getting my coordinate system correct. Yep, moment, so then around here, it'll be this distance here, so that's going to be a plus 1 newton times L over 4, and then it's going to be here, I'm going to flip, minus 10 times 10 to the 3 times, that distance will be 4L divided by 5, and we can solve essentially for that moment here. So actually we can do that right now in Mathematica, at least kind of in the outset. So I'm going to define our f of y. I'm just going to quit the kernel here. I'm going to bring this to the side. Oops. There we go. It's just clearing, making a memory, and then we're going to solve for this system here. Uh-oh, come on. Let's go ahead, we're going to just, even better, we're going to close the notebook and we're going to restart. I'm just going to clear everything here. Good. So let's go ahead and click this here. We'll restart this here. We'll open the notebook and we'll get those parameters solved for. We know the boundary conditions at this L, no displacement, no slope of our displacement function. We know that there's no restoring moment here. And we can solve for a variety of different, and actually we're going to need to do some cuts. So while Mathematica is opening up, let's go ahead and let's start to make cuts. So if I look at this system here, and I make my cut, and actually I'm going to just draw it out like this. So if I make my cut, actually here, I'm just going to open this. So if I just make my cut here, we're going to be all balanced out, right? So actually, if I look at my kind of shear moment diagram and my bending moment diagram, I would probably expect, again, now if I make the cut, that basically it would be 0 up until this point. And the bending moment here would also be 0 up until kind of you make that cut here. But once I make that cut beyond that force, actually, we're going to have to then start to map it out. So if I make my first cut here, I'm going to have a system that looks like this, where I have some 10 kilonewton here. Then I have some, basically V here, some moment X here. There's some distance here, X. And then I'm going to have, there's no restoring moment there. And I can solve essentially for what the new basically V will be, and that will be, so sum of the forces in the y set it equal to 0, and then we're going to say that this is equal to minus, let's go ahead, is equal to minus V plus 10 times 10 to the third, so that's going to be equal to V is equal to 10 times 10 to the third newtons. So that's going to be that will be that shear moment once we kind of make this cut here. So we're going to rise up to 10 kilonewtons, and it'll just be a flat line here. If we calculate the moment of x, so some of the moments at this position here, some of the moments x, or some of the moments must be equal to 0, equals mx, and then we're going to do minus 10 kilonewtons times, or 10 times 10 to the 3 newtons times x. So that will be essentially the function from here. So your bending moment, we'll switch that around. It'll actually increase, and that makes sense because we're positive curvature. So again, you can start to kind of sense what and how the cuts are going to behave like. So we can go ahead and let's start to solve this out. So I'm going to pull up the beam. Oh, it's still not responding. Oh, Mathematica, why are you having trouble today? Don't worry, we're going to close it. I'm going to open it up here. Sometimes it doesn't like to start from the startup, but I'm going to force it from my downloads. And you can extend, and then you know what the other cut would be. So basically now you'd have this plus, this minus. So you'd basically have it would drop slightly to like 9,999. This would still be increasing. And then right basically at this last, actually we can kind of look at it, the last cut, we could actually define what that moment's going to be as well. And actually we already do know, we've already calculated actually that moment here. So let's go ahead. Come on. Let's see if Mathematica is still trying to solve or to open, or if it's just giving us issues and we may have to restart. Let's see. So it wants to start. Maybe if I plug in and give my computer a little bit of juice, it may want to kickstart Mathematica. Let's see what we got here. Great. So I'm going to do, let's just do new notebook. Fantastic. You see, here we go. So now I'm going to do open recent. I want the beam bending exercise. Great. So I'm going to set up this expression. Let's set it up here. So PET, so that's 1, length 100. Great. It's all kind of set up already in this notebook. I'm going to define essentially my value. So it's going to be 10 times 10 to the 3 Dirac delta x minus L over 5. Because I've set that equal to 0. It's plus. I'm going to do minus 1 times Dirac delta times x minus 3 L divided by 4. My boundary conditions, I'm going to set it up as such. My y of L equals 0. My y prime of L equals 0. My y double prime at 0 equals 0. And I can say that initially, at this position here, at y equals 0, there will be no basically shear force. So that's one boundary condition that I can actually specify. And we're going to actually test this with multiple boundary conditions here. So we can now solve for that differential equation. And let's go ahead and copy and paste that here. And put it in here. And we'll confirm. Let's see, what does our... Excellent. Looks right, correct? So we push up on the 10 kilonewtons, so we're having a large displacement here. We can go ahead and click on the find maximum. So let's go, instead of find minimum, I want to find maximum. And then I want to start, let's start at 0.1. You may start at 0.01. So that 0.8, let's look at our moments. So we should expect, again, probably a moment that is, again, we're bending up. So we should have a positive moment, bending moment at our location here, which is excellent. No moment here, makes sense, fantastic. We could find essentially, again, the maximum here. Find maximum, we can search at L. So we have this here, makes sense. So if I look at now the top of my beam with a positive moment, should be in compression, we get that. Let's look at our shear diagram. So our shear looks like this, and nothing. And then if we look closely here, so I'm actually going to set up, because we know this should be 10,000 when we hit 3L over 4. Actually, we can just look at it like this. Exactly. Shear at, let's just do shear at 3L. Actually, let's do 3.1 L over 4. So right when we go about at that cut, we should have, I think, a shear of positive 999 or 9,099, and indeed we do. And actually, we can look at that all the way. Shear /.x goes to L, and we should have that as well. Excellent. But if we go less than, so if I, for example, do again 1.1 L divided by 5, I'll have that 10,000. Excellent. This makes sense on that kind of shear diagram and from our diagrams here. So we plotted it in terms of the shear. What about if I wanted to look at the moment? Well, the moment we've already calculated, I believe somewhere, but if not, we will actually look at it right now. Our moment is equal to, let's solve for that moment right here. So my moment at the edge will be solve, because I want mx. So sorry, I'm just looking over here. So let's go ahead and solve for that moment. And then there'll be a little moment mx here. So we're going to solve that mx is going to be equal to, and actually I'm going to define my moment as well. We defined that our moment from our, let's see, I'm going from our statics diagram, that our moment is equal to this. So I'm going to call this my mom at the edge of that beam, that capital M. I'm just going to call it capital M, equals, let's go ahead and solve. 0 double equal M plus 1 times L over 4 minus 10 times 10 to the third times 4L divided by 5. So that's going to be our moment, capital M. So capital M looks like this. And then we're solving mx. So we were saying for this particular, we're doing the shear and the moment here. So we were saying mx after that cut. Make sure we know what that moment is right now. Because if we cut at that, right at that boundary, we can kind of see what it is. But actually, we know right at the boundary it must be equal to that. So if I do y double prime this, my moment, let's see if it changes our solution at all. So I'm just going to put this one here. I'm going to put this in here. And then this. Oops. And this is where, again, we got to be careful. Because, so let's actually look into this a little bit. If I make that cut at some distance here, so let's go ahead. I'm making this cut right here. I'm going to have this minus V. I'm going to have some moment mx. And then I'm going to have a force here, which is 10 kilonewtons. I'm going to have a force here, which is 1 newton. And actually, the moment there will be positive, but it's going like that. Let me see. I see. I made a, so do your problem slowly. Y of L equals 0, y prime of L equals 0. I need to set this equal to 0 here. So at the edge it's this. And then now I'm saying at here it's equal to L. So excuse me. And now hopefully that will work. Control C, Control V, Shift Enter, and I'm going to put this here. And now we're back to it. So excuse me, we didn't have to even go through that. I just wanted to double check. But so we can use that moment definition just as we did previously. So we know at this position here, no deflection, slope is 0, moment is equal to that, and then finally we got that value here. We can double check our solution, looks good. Moment is still positive, which makes sense and consistent. And even if we just stick with these definitions, we will get our same old and good old shear diagram here. But there you go. So I think this is a good way to kind of look at and solve some of these problems. And yeah, we'll see you all in the next video. Thanks. Bye.